All right. So it's our pleasure to have here our next speaker, Vitor Barroso Silveira. Vitor is a PhD student at the University of Nottingham with Silke Weinfurner, and Vitor is going to talk about primary thermalization mechanism of early universe observed from Faraday wave scattering on liquid-liquid interfaces. Vitor, whenever you want, the floor is yours.
Yeah, thank you. So again, thank you for organizing with Silke. I'm sure she would like to be here, but I hope I'll make justice with this presentation. This very long title is actually the title also of our paper that is now on, well, the preprint is on archive and current waiting for submission. So I'll briefly start by introducing some of what is analog gravity for those who are not familiar with it, and what are the problems we are tackling in this project, which are related to cosmology. I put here, one second, yeah, okay. So I put here Bill's original paper from 1981, experimental black hole evaporation, which I would consider started the field and set the tone for what we do nowadays, right? In a few words, what we do in analog gravity is try to find, if you will, down-to-earth systems such as fluids or other condensed matter systems to mimic and simulate gravitational effects or quantum fields propagating around gravitational and cosmological scenarios. And by doing that, for example, what we do here in our lab, by taking a fluid and studying how small fluctuations on the surface of this fluid behave, we then describe the dynamics of those fluctuations through an effective field theory in flat or curved spacetime, depending on the analog you want to study or tackle. By doing so, we usually assume a minimal coupling with gravity, and generally, but maybe not always, you disregard any mode-mode interactions or any sort of nonlinear effects in your fluid. Well, since Bill's original paper, a lot has happened in terms of theoretical developments, but also experimental developments, especially in the past 10 years. Here I mentioned the case of Jeff Steinhauer, who measured an analog of the Hawking effect in BCs, and really an example of our lab in this work done by my colleagues with Silke as well here in Nottingham. Well, but what everyone wants to ask, at least when we talk about analog gravity, it's sort of the elephant in the room, if you will, is what can we really learn about these gravity simulators, about these analog gravity experiments? And I'll refrain myself from entering a very long philosophical discussion, but I'll try to answer this question with what I think are the main things we can tackle with these experiments. So the first of them would be realizing abstract ideas and testing conceptual theoretical models, for example, and by doing so we can gain practical experience, really hands-on experience on this phenomenon. And while doing so, we are effectively cross-validating theoretical toolboxes. So really using both using both okay, sorry. Using both methods from the description of the system, so for example, hydrodynamics and condensed matter, but also from general relativity or quantum field theory in curved spacetimes, for example. Ultimately, I would say that in these experiments, we're searching for new observational signatures or new signatures of these phenomena that we are studying or attempting to realize. But going back to what I said before, all these effective field theories and these approximations really that we do, they might not be enough to study all types of setups, and you might want to go further and, for example, include nonlinearities or even mode-mode interactions in your effective field theory and in your analog. So, and that's how we've been working with Silke and all our collaborators into trying to realize a gravity simulator that can really simulate what eventually you might not be able to calculate with your effective field theory. So for that purpose, the fundamental physics question we're trying to solve is related to cosmology, and that was really a choice we made. And briefly describing the background of it, in the history of our universe, after inflation, after this very rapid expansion of our universe, we were left with this cold and dark universe that eventually had to be thermalized, and so then the nucleosynthesis could begin. And this thermalization process has been theoretized and it's referred to as reheating. So really a warm up of the universe after inflation. Now, the initial state of this warm up of the universe, of this thermalization process, is referred to as preheating, and that's the physical question we are tackling with our gravity simulator, or cosmological simulator, if you will. In a single field model for inflation, you have this inflaton field here, which is represented by this blue ball, rolling in this fairly flat potential while inflation is ongoing. And by the end of inflation, it falls into a minimum of its potential where it oscillates. And while oscillating, it efficiently transfers energy to other fields that populate our universe, be it other particles or quantum fields that are just hanging around. And that efficient transfer of energy is then what starts creating particles that will lead to this thermalization process. But then to encompass what preheating is, in here 2 bullet points, if you will, I would say the first part is this harmonic oscillation of, or this repeated oscillation of the inflaton field around its potential, its minimum, causes parametric instability. So it parametrically amplifies these other fields that it couples to. So it sources very efficiently the amplification and creation of other particles. But then these parametrically amplified fields, they grow and grow in amplitude until nonlinear mechanisms enter, and through these mode-mode interactions, be decays or scattering process, more particles are created, then leading to this full thermalization process. So keep in mind, because I'll bring this all back, but what we're thinking here is preheating dynamics as a matter of a primary instability caused by the inflaton field in a daughter field, if you will, and a secondary instability caused by nonlinear interaction between all these other fields that we are studying. But then how do we experimentally implement this preheating simulator? Well, we chose to do it in a fluid interface. And ultimately, what we're really doing is attempting to recreate an effective field theory simulator. To do so, we believe we need 3 things. So one of them is control, so we can tune the parameters of our experiment and hence tune our effective field theory. We need precision in the measurements we make, so we can rely on the results of our setup. And we also need repeatability. So we want to be able to repeat this experiment as many times as possible to extract ensemble properties, statistical properties, and then use the entire machinery of field theories and statistical analysis. Well, our system, just to give you an idea, is an immiscible 2-fluid system. These 2 fluids are confined in a donut-shaped tank that looks pretty much like that, about 10 centimeters in diameter. The interface of these 2 fluids experiences an effective dimensional reduction. So you can write it as a 2D interfacial dynamics, and our analog field, if you will, are the fluctuations around the resting interface. And once you shake this system, waves start appearing in the interface in a process called Faraday instability. So if we harmonically oscillate this tank of two fluids, eventually waves will appear, and they will experience actually an unstable dynamics that to a linear level looks pretty much like this, a harmonic oscillator with a time-dependent frequency, where this f of t here that enters that frequency is playing the role of our inflaton field. Now, we want to see how these waves form at the interface. So in our setup, we put this tank on a bespoke, really made in-house here in Nottingham shaker, and we see how the system evolves. And to do so, we use a backlit checkerboard pattern that looks pretty much like this. And by the way, that pattern, the picture of this pattern deforms over time. We can then reconstruct the profile of the interface over time. As I mentioned before, we want to repeat the experiment. So in this case, we repeated over 1,500 times for about 50 hours, where each repetition took on average 2 minutes. And just to really more clearly display what a repetition looks like, what I call a repetition or an experimental run. So here, hopefully you can see the video. It might be a bit laggy, but on the right-hand side here, in red, you can see the position, the measured position over time of our shaking plate that I showed in the previous slide. And here in blue, you can see the reconstructed data from one of these experiments. As I mentioned before, we expect that waves will eventually appear at the interface and experience an unstable growth. So really an amplification in a fairly known way. And they appear as standing waves in the azimuthal direction, as you can see here. And as they grow larger and larger, almost reaching really the top and bottom plates of the container, we expect that nonlinear mechanisms will enter in play there. And we label these waves that appear in our setup by the amount of crests they have or troughs, which those we call the azimuthal number. So this M here that labels the mode, the interfacial mode. In the experiment, in all 1,500 runs, we find 4 crests, meaning then that we are studying the azimuthal mode M equals 4. It doesn't mean that other modes cannot appear in the system, but this is the dominant one. And through some data analysis tools, we decompose this evolution of the azimuthal mode into a frequency-dependent component and a instantaneous amplitude, which are these B's. And these B's will be the central feature of our entire analysis, really. Now, quickly going through how we interpreted these results and did the data analysis of it and reconnected it to preheating ultimately. So as I mentioned before, we had that tank sitting on a shaking platform. We shake it 1,500 times with a shaking profile that looks pretty much like this. This is one example from a realization. And our interface evolves like in that video I displayed before. Now, what we identified is that our interface undergoes 4 distinct stages, or at least 3, if you want. And initially, you have a random noise at that interface that will get amplified by our inflaton field, which is the shaker, right? Now, by realizing it over 50 hours, that initial state changes, and you can see that those B amplitudes, they spread throughout several orders of magnitude. And each of the very thin blue lines here is one repetition. But what we see in all of them is that after our detection method, whose I would say the threshold at about 1 micrometer doesn't allow us to see what happens before this point. After that, we see a very clear log linear growth with a subsequent log linear decay, which is related to damping in our system, which is always very strong. What is surprising to us is that if this was a linear evolution purely, we would expect this wave to just continue growing. And as you all know, the vertical confinement does not allow that. So somehow our effective field here, psi, has to experience something blocking its amplitude, which is what we see here. So this stagnant yellow region for the runs whose amplitudes get as large as 1 millimeter. Then we looked in more detail here through the eyes of hydrodynamics. So essentially tying it back to what I mentioned before of cross-validating different toolboxes. Here we went for a work that Miles did in the 70s on hydrodynamics in describing the dynamics of surface waves with nonlinear effects in closed systems, exactly like ours. We had to extend our results to his results to a two-fluid system. And essentially, his idea is to assume a variational ansatz where he obtains a Lagrangian expanded in small amplitudes psi A, B, and C here, which are different modes of the system that I mentioned before. And these coefficients here of his expansion are determined by the spatial profile of each one of these. So really the amount of crests in the azimuthal direction and how the wave looks like in the radial direction. Now, by looking in more detail of what we really see in the experiment is we have two main cases. The first one is a self-interacting dominant mode in which the wave gets so large that it triggers a fourth order, a quartic term given by this. These terms vanish. And we know that by simply computing these coefficients from experimental data. And with that, we model the dynamics of this dominant mode truncated by certain parameters. And the other option is to look at secondary modes or subdominant modes, if you will, that interact with this dominant mode in a way that essentially the big M=4 wave that you saw before starts sourcing the instabilities of other modes that sit in the system. So other azimuthal waves and radial cross sections. But now that we have this nice looking effective field theory, the question is, do we really understand it and how to reliably test it? And for that, we had this, we still have this collaborator in Vienna, Sebastian Ern, working with Jörg Schmidmeier. And in some of the work they did there, these two that I mentioned in my presentation, they show how to extract effective field theory descriptions from these cold atom systems, from experimental systems. And inspired by that, knowing that we couldn't get more classical with our setup, these are just two fluids at room temperature, we repeated the experiment, as I mentioned before, so we could use higher order equal time correlation functions. And that was really to understand really the distributional properties of our ensemble of repetitions. Our choice was to use the connected correlation functions divided by the full correlation functions, which are a measure not only of Gaussianity, but also of changes in linearity in our setup. And the quantities we compared are our theoretical values for this quantity and the experimentally extracted quantity M4 and 6. And what we see here is that our self-interacting dominant mode agrees fairly well with the experiment, showing that that effective field theory borrowed from hydrodynamics has some sense. And when probed in a statistical experiment, so an experiment where you repeat it and you can extract the statistical properties of it, it matches the results. But again, this is only for the dominant mode and for the primary instability, if you will. And for the preheating dynamics, you remember, hopefully, that one of the main features was the appearance of secondary instabilities. And those secondary instabilities, they would appear at different frequencies and momenta as well. So what we did was to look not only at the primary instability.
5 minutes.
Yeah. At the primary instability with low frequency, but also the secondary instability with higher frequency. What we see here, again, with our model in red and experiment in black, is that our model for one repetition here, as an example, agrees very well with that stagnant amplitudes that I mentioned before, but it also agrees with the appearance of secondary growths in our experiment. And when we looked into detail at the momenta of these interactions, we see that at early times, we have a very strong occupation of low radial wave modes that then later on, when mode-mode interactions are triggered and nonlinear effects get more relevant, the occupation starts spreading out for lower momenta and occupying higher momenta. And that is a strong feature of not only our model, which is effectively a phi-4 model, as it only keeps fourth order corrections for the Lagrangian, but also it shows that we can point out specific decay channels, if you will, in our setup. And by comparing that to theoretical previous work on this analog, BC analog for preheating from Zache, Kasper, and Burgess, they proposed a different type of preheating, of simulation for the preheating dynamics, in which you have these two species condensate, which through decay creates a primary instability. And then those primary instabilities trigger secondary instabilities at specific channels, which they very elegantly describe through these Feynman's diagrams. So then through their effective field theories, through their analog model, they show that the growth rate of the secondary instabilities is not just a random number, but it's directly related to the growth rate of the primary instabilities, in particular 3 times. And that is because they compute this value through their effective model, which is through the Feynman diagrams. And we try to do some of the same, not computing Feynman diagrams, but comparing those growth rates and see if our phi-4 theory, just like their phi-4 theory, could display this feature. And in fact, in our model, we see that the secondary growth rate, which you see here in ensemble distribution, agrees reasonably well with 3 times the primary instability of our method. Now, to recap very quickly what I just showed you, what we try to display here is that through analogs, we can observe these emergent effective theories, and in our case, build it from hydrodynamics, and with that, simulate the preheating dynamics. So in particular, the decay from a primary instability to secondary instabilities, but not in a random way, but to specific momentum and frequency channels in ways that we can really predict even the growth rate on average or on ensemble property of those secondary instabilities. We hope that our results eventually display universality and robustness of this preheating dynamics in a system that is extremely damped and has strong interactions between all the modes. And I guess the question we're trying to raise in the end is, can we use these analog systems? Can we think of simulators that can really calculate what are maybe the most elusive processes of our universe? with that, thank you for your time, and I'm open for questions. Yeah.
Thank you, Peter. Thank you. All right, we have time for questions. Masahiro.
Thank you very much for nice talk.
Hi.
Very interesting. For realistic preheating procedure in our universe, one of the main interests is reheating temperature after preheating. So can you evaluate such a reheating temperature by using your experiment? In some sense, it's an analog sense. So can you directly measure what can you evaluate the reheating temperature?
Just to see if I understand your question, can we extract a preheating temperature from our experiment?
Yeah.
I don't think so. I don't think we looked into that. It's a fairly interesting question. It is what I would say is done in when studying Hawking effect analogs, right? Trying to extract this temperature. I don't quite see how that would work here. We're at room temperature. These are large waves, and honestly, we can't even control precisely the temperature of the experiment itself. So it's definitely something I would look into, but would be a bit skeptical that our setup could do it. Yeah.
Okay, thank you very much.
No problem.